we're right on schedule to start chapter 4 today, common elements. So that's probably that's what they call it in the book. That's referring to hydrogen being a diatomic. Do you remember the diatomic 7? So they make a 7 on the periodic table with a 7 shape. And then hydrogen is number 7. So it's nitrogen, oxygen, fluorine, chlorine, bromine, and hydrogen. And then the structure of atoms. So you have to know about protons, neutrons, and electrons, their mass and their charge, and where they're located. Protons and neutrons have a mass of 1, and they were inside the nucleus. Electrons have a mass of 0, and they're outside of the nucleus. And then protons have positive charge. Protons determine which element we're talking about. Neutrons have no charge, but they do have mass. So those are part of the mass number. So understanding that symbol with the A and the Z, the mass number and the number of protons. So just like we did on the worksheets. So let's say that there's a quiz that in class I would give 15 minutes. And usually that's like the slowest students, maybe 2 or 3 students are still working. Mm-hmm. So for some students, they might finish in 5 minutes. Mm-hmm. Almost everybody's finished in 15. Or some people want to just make sure and look it over. Mm-hmm. How long should that have on the computer, do you? I've added 10 extra minutes for every quiz. 25 minutes for a quiz that normally is finished in like 5 or 10. So that gives a little bit of extra time to work between the screen and the paper and to figure out how to get all the answers entered or if there's internet connections. Okay, so today I want to start talking about energy. So we may have talked about energy before. We can apportion energy in different ways. And one of the important ways to be able to think about energy is in terms of kinetic energy and potential energy. So some of you may have seen this before in your physics classes, and for some people this may be completely new. So kinetic energy is the energy of motion. So when something is moving, it has kinetic energy, and that depends on how fast it's moving, the velocity. So that would be the V. Oh, let me get my toolbar. That would be the V in the equation right here. It also depends on the mass, so that's the M. So how much something weighs and how fast it's moving determine the kinetic energy. And so it has to be moving, it has to have a velocity. In the picture here, when somebody is holding this ball A, if he lets go, it's going to roll down the hill. And when it's rolling, it will have kinetic energy. So while he's holding it right now, it's got stored energy. Because it's up the hill, it can fall down. It has that potential. So that has potential energy. As it rolls down the hill, it has kinetic energy, and then it's going to hit particle B, ball B, and it's going to transfer kinetic energy to B. So A is going to give up its energy and give it to B. B bumps up, and A comes to rest. So now A does not have any kinetic energy or potential energy. It gave its energy to B to move it up that little hill. So there's a transfer when they have that collision. I also want to talk about thermal energy. Thermal energy is just the kinetic energy that we have by virtue of being at a temperature. So here's our temperature component. You don't really need to know how this equation comes into being, but T has to be in Kelvin, absolute temperature, and the K is a constant, it's Boltzmann's constant. In each direction, X, Y, Z direction, we have 1/2 kT, and that's why we have a 3 on top, because there's 3 directions of motion. So at a given temperature in Kelvin, we have a certain amount of energy available, and that energy will be reflected as kinetic energy for particles moving, and that gives us the measurement of temperature. So we're really going to weave this together with some of the other conversations we've had about energy and the motion of particles. So remember, solid, liquid, gas is very much related to the motion of particles. So we can talk about at a given temperature, there's a certain amount of thermal energy. And that will help us determine for any substance whether it is a solid, liquid, or gas at that temperature. So when we talk about a solid, those particles, they're not moving a lot. They don't have very much kinetic energy, very small kinetic energy. And right, they're locked in a position. They can vibrate, maybe they can shake just a tiny bit, but they can't go flying around. If you look at a gas, that has a lot of kinetic energy. They're moving through space. And here it's having a collision, it hits the wall and bounces off. So gases have a lot of kinetic energy. When we look at a solid, it's at lower energy, and most of its energy is potential energy. So it's the interactions between those particles you could think of like stored energy, potential energy. In a liquid, these are moving, so they have kinetic energy, but they're also close together, so they have interactions with their nearest neighbors. So they have kinetic and potential energy. But in the gas phase, those particles are so far apart, there's no interaction. They're just flying around like they're by themselves. So they have essentially no kinetic energy, no potential energy. All of their energy is kinetic, the motion. So we can think about, here we've got a flask with water in it. And at that surface, down below we have, I don't know if you see the mouse, let me get my spot back. Down below we have the water molecules close together in the liquid. And then at the surface, if they have enough thermal energy, they can actually leave all their friends, all those other water molecules, and escape into the gas phase where they're by themselves. And then they are in the gas phase. So this transition from liquid to vapor is one of the things that we'll talk about. That transition happens, it happens at many temperatures, but it happens spontaneously when we're at the boiling temperature, right, to go from liquid to a gas. So I think I've shown you this little chart before. At a temperature, so this is an absolute energy scale, the solid is always lower in energy for any substance than the liquid of that same substance. And the liquid is at lower energy than that same substance as a gas. And let's see. For the units of energy, we use two, basically. We can use the calories or we can use joules. Joules is the SI unit. Joules are pretty small. It's a small amount. 1 calorie is a small amount of energy. When we look on the label of our food, we have a capital C, and that's actually a kilocalorie, 1,000 calories. So in the lab, that's one of the issues we take a look at, calories versus nutritional calories. In that energy lab, we burn some food, and then we try to calculate how much energy is in it. Okay. So a calorie is the amount of heat it takes to raise 1 gram of water by 1 degree Celsius. So it's a very specific amount of energy. So I want to talk a little bit about how reactions happen, just as we're setting the energy, how we think about energy, how we look at energy on paper. So when those molecules in the gas phase come together, they have collisions. Anytime we have a reaction, there has to be some kind of contact made, some kind of collision. So in the gas phase, those particles have to find each other, but also in the liquid, they're there's water molecules, there's other molecules there, but they have to move through the liquid and they have to come into contact in order for a reaction to happen. So you can see in this picture, let me get my little light. You can see in this picture, in order for that oxygen to go from the ozone onto the NO to form this new bond, it has to be oriented in the right direction. It has to come together, it has to have a collision, it has to have enough energy to break that bond, and it has to be oriented in a way that the reaction can happen. So if they collide like this with the oxygen pointing towards the oxygen, they could have a collision that is strong enough to break the bond. But because of the orientation, they just reform the original reactant. It doesn't go to products. So we can envision this system as an energy diagram. So this is a way that we can talk about energy in a very intuitive diagram format. So on this side over here, we have increasing energy. Now, it's not necessarily, if we're looking at a chemical reaction, we're not looking at Kelvin particularly. We could be looking at kilojoules per mole, and it might be a smaller amount of energy than a whole Kelvin. So, let me move this guy. All right, so we have this line. This represents whatever the energy is of those reactant particles. So the ozone and the NO, just some amount on the scale from low to high. We just draw a line. So if this is the energy of the reactants, they have to have a collision that has enough energy to get up over this activation barrier. So they have to have enough energy when they hit to break the bond and form that intermediate where it's half broken and half formed. Now up at this top part where that bond is broken, it could either go back to the reactants because the orientation, it didn't go to products, it just went back. Or if the orientation was correct, it could go forward. And in this case, that energy of the products would be lower than the energy of the reactants. So we can tell because it's down low on the graph. So we're going to look at that energy difference. This much energy would be released, usually as heat. And that's what the lab takes a look at. When we touch our test tube, we can feel whether it gets warmer or colder. So in this case, all of that energy would be released. And that would be the heat out. The heat comes out of the reaction. It gets released. And that's why we burn things, right? That's why we make a fire, we build a fire to get warm. It releases heat and it heats the surroundings. So some other issues here that are confusing is the reaction product progress. So you could think about this, it's an abstract concept. It's not always physically real. So one good way to think about that for a reaction is that molecule, the O, breaking its bond and moving to the product. So that's one way to think of the reaction progress. That can be sometimes a little bit confusing. All right, so let's talk about the energy of light. And the reason we have to talk about the energy of light is that light energy is how we know everything about the electrons and where they are in the atom. So our understanding of the structure of the electron orbitals is based on a very small amount of data. It's quite amazing to think about how much was determined just from the light that was seen, was observed. Okay, so we have to understand how light works in terms of energy. We call it the electromagnetic spectrum, electromagnetic radiation, because every time you have an electric field, you also have a magnetic field. They come together always. So we have all these different regions on the electromagnetic spectrum. And what we see is just this little sliver where the rainbow is. That's what our eyes are able to detect. But as we go up, if you think of going up to the right, these ones, the waves get longer and longer and they have lower energy. So you could think about on this side, if you go and you get some French fries and they have that red light over the French fries, that's to keep it warm. The IR area of the spectrum is heat. That's just radiant light. It's light that makes things warm. So that is infrared. Some of it we can see as red light, but even when we don't see it, it can still make things warm. You might feel this coming in the window in the sun. You can feel that it's warm even though you don't see the red color. That would be the infrared that you're sensing. Now, as we get longer and longer, we get all the way down to radio waves. These guys can travel around mountains. We have our AM frequencies, our FM frequencies. And then as we get shorter and shorter wavelength, our frequency is higher. These have more energy. And we get all the way down into X-rays. So UV, on the blue side, ultraviolet, this is where we get the sunburn from the sun. So that's enough energy to actually damage our cells. And we get to X-rays, it goes right through our cells and it hits the bones so we can see bones. But it's also damaging. That can cause changes in the cells. And we get all the way down to gamma rays. These are in the order of particles, like radioactive particles are emitted, or there's a lot of background frequency in outer space. There's gamma rays out there. So these are high energy. And I always remember that because of the rainbow. On the red side, it's nice and warm. And on the blue side, ultraviolet, that's where I get really burned in the sun. So this is the low energy and this is the high energy side. Okay, so let's talk about how we use that electromagnetic spectrum to find out information. Here is the very large array. And you can see here, there's a little van. There's an RV for research there. So these are actually quite large, right? Very large array. When we look at the galaxy, right, we look in the optical range of our eyes, we see this big fuzzy blur. And what do we see? We don't know. But if we tune our detector to match the system, and then we use colors to make it so we can tell the difference, so we map on a rainbow color spectrum, now we see a lot of finer detail. That bright spot has a very small center that's emitting all that light. And then up here, it doesn't look like much, but you can see from this radio spectrum that there is a bunch of detail in there, right? So when we think about using light, we really can think about tuning our flashlight to match our system and to match our detector. And for us, the detector is the eye. So if you want to look in the closet, you're going to use a flashlight because that's the light that will bounce off your objects in the closet and you'll be able to see them. Here's an infrared image. So the black bag blocks us from seeing the man's arm, but if you look in the infrared, you can see the heat coming out. You can see that his hand is brighter than the part he's wearing long sleeves, so that blocks some of the heat, but his open skin is the hottest, right? So we want to think about light as tuning our detector, tuning our flashlight to match both the system and also the detector. So how do we know what we know about electrons in atoms? Well, we can take, the way this was done was looking at discharge tubes like a light bulb. So it's glass with a gas inside. and then we put electricity across it. That electricity excites the gas, bumps it up to a higher energy level, and then because it's at a high energy level, it's gonna just spontaneously relax back down. So that's gonna relax back down, and when it comes down, it releases light. So we add electricity, it excites it, and then when it comes down, it automatically releases light. This is how neon lights or fluorescent lights work. But that color of the wavelength, that color of light, tells us the energy of that photon. So from those colors, we determined the distance in energy between those two energy levels. According to this equation, oh, that's one of the symbols is not showing. I don't know what the diamond is. I think it was an arrow originally. So we have the energy of light. We didn't talk a lot about all the mathematical details, but we have our wavelength is lambda, and then h and c. C is the speed of light. H is another constant. But we can go from that wavelength to an energy in joules. And that corresponds to the distance between these two energy levels. So this is literally how the original theories of the atoms, of how the electrons behave in atoms, was determined. And from it, we get this kind of a model. So in here, some of these will be familiar. This is what? This is the nucleus. The nucleus is very small. It's got all the protons. So now we're talking about the electrons in the outside area. And we can use, this was for hydrogen. We can excite those hydrogen atoms up. So here's the excitation. Some kind of an energy comes in. Maybe it's light. Comes in, and now it's excited up into the n equals 3 stage, right? These are our n values. And by itself, it just relaxes back down. Now, when it goes from n equals 3 to n equals 2, it gives us a red light. And from all of these, if we look at n equals 3 to n equals 1, that gives us another color. And that gives us our line spectrum. So this is what we see. This kind of a spectrum, you see how only some lines are showing. Those correspond to these transitions. So if we had continuous light, like a light bulb, we would see all of the colors, the whole rainbow. But because these electrons, they only make certain jumps. They only get one energy, right? They just get that one line. Usually we can see the blue-green one, but for many people, the violet is not visible for their eyes. So it depends on how you see it. It depends on your eyes too. Usually in the lab, we only see 2 lines, but there's some more right here for these transitions. So just based on that line spectrum, which these are pretty easy to make, right? You can just turn on the light and you have a grating and you look through. Very easy to look at even, 100 years ago. And from just these lines, all of this theory was developed about how electrons, how they interact and where they live, where they spend their time around the atom. From this information, they found this distance, 0.52 angstroms, is the same. That never changed even in all of the development. So the energy of these levels and the distance from the nucleus were all determined just from this information. It's quite amazing. So this is what we're looking at. We're looking at the nucleus, and then these are the orbits around where the electrons live. And we can put them on an energy diagram from low to high. And the inner ones, the n equals 1 is low, n equals 2 is higher. So you can think of it going up in this way. Here we can see, oh, I don't have my spot. Here we go. Here we can see that first energy level has a smaller distance. If we go from this one, the green, that has a bigger energy, a bigger distance on the energy scale. So it's more energy, it's going to be on the green wavelength. And then this one has even more, and it's blue. So that's how those colors related to the energy levels. We use that emission spectrum of hydrogen to determine the energy levels for a hydrogen atom. This gives us the Bohr model. The Bohr model says that we know how many electrons are in each orbit based on what number orbit is. N equals 1 has 2 electrons. N equals 2 can have up to 8 electrons, and N equals 3 can have up to 8 electrons. Now, bigger atoms are not adequately described by the Bohr model. So the Bohr model really works for these elements up at the top, up to argon. When we get down to these ones, it doesn't work as well. But in order to make any changes here, we actually had to develop quantum mechanics to figure out how atoms are moving in multi-electron atoms. Sorry, how electrons are moving. So the Bohr model says these are particles. The electrons are like circling around just like planets. We know how many electrons, the maximum number of electrons based on the N value. And we know how far those orbits are from the nucleus. So in order to make so this works really well for 1 electron. But when we have 2 electrons or more, then the electrons interact with each other. And that was a major step forward in theory when we learn how to deal with that. So that requires the quantum mechanical model, which treats electrons as waves. And waves, if you think about dropping a pebble into water, rings come out. So if you drop 2 pebbles, rings spread out, and then where they meet, it makes an interference pattern. So in order to include the interference pattern of 1 electron interacting with another electron, we have to use a wave mechanics model. From that math, solving the 3-dimensional wave equation for electrons in the potential of a nucleus, we get orbitals. So we're going to change our language here and talk about orbitals. So this is what is accepted for describing where electrons spend their time. This is a probabilistic model, which means we're really wondering, where are they likely to be found? If we look at any one time, where are we likely to find them? So when we describe this location information, we really are deciding to draw a boundary, right? The blurry photo, right? This one shows like if we take a measurement, where did we find it? Okay, maybe right there. And we take another measurement, they're more likely to be found close to the nucleus, but there's some probability out here. So we decide to draw a line at the 90% probability. They'll spend 90% of their time in that space. 10% of the time, they could be somewhere else. Electrons are squirrely, right? It could be in China, we don't know, right? So we just draw this 90% boundary, and that's what we call the orbital. That gives us the shape and the distance from the nucleus. So in this orbital, this is a 1s orbital. It's spherical. That's why it has the S. So it's spherical shape, same probability in any direction, X, Y, or Z. And we're saying we're 90% sure that that 1s electron is inside there. That's where we're likely to find it. So I do like to take a couple minutes to talk about the nature of electrons because it's fascinating, right? This is where the mystery of chemistry is. So let's talk about that wave behavior. When we think about a standing wave, so a wave can travel through space. Like you put the pebble in drop it into a fountain, those waves travel away from where you drop the pebble. So they move through space away. Some waves are standing waves and they stay in one location. So an example of that is a stringed instrument, because right where the fret is, right where the bridge is, it holds the string down. So that one will never go up and down. It's always at zero displacement. Down here, the string is also pulled tight over a position that's always zero. So to make a sound, to make a wave on that string, we can get only things that are zero on the boundaries. So we could have half a wavelength. We could have a full wave. We could have 2 halves. We could have 3 halves. But we cannot have a wave that has a high peak in that position because the string is held down. So that's a standing wave. If you think about that orbit, we can think about 2-dimension circle. We have to make those boundary conditions match each other. So we're going to bring those together and get standing waves. I think I've got one more. Yeah, so here they match. But here, if there's a mismatch, then that cannot exist in the circle. And that's the same kind of thing when we mathematically solve for the orbital functions. It's 3 dimensions, but they have to obey those boundary conditions in 3 dimensions. So in this is still 2 dimensions, but we can see if we touch these together in a circle, we get something that still can have a standing wave. But if they don't match where they come together, then there's no standing wave that can exist there. So let me just go back and watch this video. This video is very cool, and you can find this from the lecture slides if you want. And I think it is this one. Okay, so what we're going to look at here is it's a 2-dimensional drum. So you can see it's just a stretched material, and it's connected to a speaker. And the speaker is going to vibrate that membrane like a drum, and they're going to put sand on top. And the sand will stop in the nodes where the membrane is not moving. So if it's moving up and down, it's going to push the sand away. What you see now, these lines, those are the nodes where there's no movement. So I'm going to start it over. We hear the energy that they're putting in starting at low energy, and it's going to go to high energy, right? And we can hear it go, whoa. That's the amount of energy that's going in. Okay, so here we're going to start, and it's just a bunch of sand, and they're just applying a speaker to the membrane. So this is a really good example of theoretically what happens when we're solving for the 3-dimensional wave equation for where electrons spend their time. Did you see how it jumped? At the end, it had very complex patterns. And then it would jump from one complex pattern suddenly to the next one. That's kind of like jumping into a different energy level. It didn't smoothly go. It would have like the tic-tac-toe pattern, and then it would go, boom, different pattern right there. Did you see that? Yeah, so I like that visualization because that's exactly what we're talking about, only for very tiny systems in 3 dimensions. It's a little bit hard to visualize, but you can see that out of that arises, there's lots of mandala patterns that might be familiar. So it's a natural phenomenon. It's very, very interesting to me. Okay, so that's basically what we're looking at when we talk about orbitals. So I'm going to give you some ways that the periodic table gives us information about these orbitals. And one is that the n values, starting at the top, right, n equals 1, n equals 2, n equals 3, those correspond to the size and the energy of those orbitals. So electrons in a 1s orbital are going to have less energy and be smaller than electrons in a 3s orbital. So those have a bigger space and they have more energy in that space. So the n value tells us the size and energy. And when we look at an element, we can tell on the periodic table, just by where it is, where its valence shell is. So the valence is the outermost shell, the highest n value. We'll be working with that a little bit next week too. So this helps us understand those trends, increasing size. So as n gets bigger, the size gets bigger, right? Adding a proton in the nucleus and an electron in the outer shells. We talked about the metallic trend. So when we talk about orbitals, we're talking about where an electron spends its time. Each orbital can hold up to 2 electrons, and each shape is designated its own subshell. Each subshell has a unique shape. So these are the shapes. If it's an s orbital, then it's spherical. It's the same in x, y, z directions. If it's a p-type orbital, it has this shape. It goes along one axis, and it's got 2 lobes. It's got a node in the middle where the electron will not be on the nucleus, right? It can't take that same space, so there's a node in the center. We also have the d orbitals. They have 4 lobes, and they get into a bunch of shapes. So we won't be looking much at the d's.